let's talk about troubleshooting protocol problems. Now, in order for two network hosts to communicate, they have to be using the same network protocol. Therefore, if you have an IP-based network with IP-based routers and servers and other IP-based hosts, and you go ahead and install a workstation on that network and you configure it with a different protocol, then it's not going to be able to communicate with any other host. Everything has to be using the same network protocol. In addition, if you do decide to use an IP protocol on your network, then your IP network configuration settings have to be made correctly. For example, all of the hosts on the same logical network have to be using the same network address. The network portion of the IP address on every single host must be the same in order for them to communicate. Now, on this network, we have 4 different hosts, a server and 3 workstations. The server is assigned an IP address of 192.168.1.1, and these 3 hosts are assigned 192.168.1.2 and 192.168.1.3, and this other host over here is assigned an IP address of 192.168.2.4. Now, to determine which hosts are going to be able to communicate with each other, you need to determine the correct subnet address. Now, if the network uses classful addressing, we can look at the first octet and determine what the default subnet mask is. Now, in this case, the server's IP address starts with 192. And because this network uses classful addressing, we know that this is a Class C address. The first 3 octets are the network portion of the address, while the last octet is the host portion of the address. Now, these 3 hosts all have the same network address, 192.168.1.0. Therefore, they'll be able to communicate with each other. Now, this host over here, however, will not because it uses a 2 in the 3rd octet. Therefore, this host is using a completely different network address of 192.168.2.0. Therefore, it's not going to be able to communicate with the other hosts on this network. Now, let's take a look at another example. Now, here, our server is assigned an address of 10.0.0.1, and this host is assigned an address of 10.0.0.2. This other host is assigned an address of 10.0.0.3, and this host over here is assigned an address of 10.200.1.4. Now, in order to determine which of these hosts will be able to communicate and which won't, we need to look at the IP address and determine what class it is. Now, again, we're going to assume that this network uses classful addressing. Well, this address starts with a 10, and if it uses classful addressing, then this is a Class A address. Therefore, only the first octet is actually used for the network portion of the address. These 3 octets are the host portion of the IP address. So in this case, the addresses are actually configured such that all these hosts will be able to communicate. This is very important because if you don't pay attention to the address class, your first inclination may be to assume that this host has an invalid address because the 2nd and 3rd octets are different. But in this case, that's not correct. In order to ensure that they're on the same network, you need to make sure that every host in the network uses the same subnet mask, regardless of whether you're using classless or classful IP addressing. Now, if your IP addresses are configured correctly, then the network portion of each IP address on each host will be the same if you use the correct mask. But if you use the wrong mask, then the hosts are not going to be able to communicate, even though the addresses may appear to be configured correctly. Remember, the subnet mask defines which portion of the address is network and which portion is node. Now, in the previous 2 examples we looked at, we assumed that all the hosts were configured with the default classful subnet mask, and that those masks were configured correctly. However, if you use an incorrect prefix, or if you don't calculate your subnet boundaries correctly, then again, communications aren't going to work. In this example, suppose we're going to use a 22-bit prefix on this network, which is equivalent to using a subnet mask of 255.255.252.0. In this configuration, these 3 hosts will be able to communicate with each other. By using a mask of 255.255.252.0, we can actually define up to 64 total subnets within this address space. Remember, 172.17 is a Class B address by default. However, what we've done is steal an additional 6 bits from the host portion of the address to create these additional subnets. Therefore, you've got to know where the subnet boundaries reside. Now, because all of these addresses look like valid Class B addresses on the surface, it's actually quite easy to miss the fact that one of these hosts is actually on a different subnet than the others. Now, in this example, our subnet boundaries are 172.17.0.0, 172.17.4.0, 172.17.8.0, and so on. In order to determine your subnet boundaries, you can use an online subnet calculator. When you do, we'll see that this host here will not be able to communicate with the other hosts on the network because it's on a completely different logical network. Its subnet address is 172.17.4.0 instead of 172.17.0.0. Now, if your host needs to communicate with other IP hosts outside of your local network segment, then there's another parameter that you have to configure correctly, and that is the default gateway router address. Now, understand that when you send information from one IP host to another IP host on the network, the IP protocol on your system will first check to see if the destination computer resides on the same local subnet or whether it resides on a completely different subnet. Now, it does this by looking at the source and destination IP addresses along with the subnet masks. If the destination host resides on the same network as the sending host, then the IP protocol will use ARP to determine the appropriate MAC address and directly deliver the data. However, if it determines that the destination host resides on a completely different IP network, then the IP protocol will immediately forward that data to the default gateway router address, and then let the router deliver the information to the appropriate destination host. Now, this can be a problem if the wrong gateway router address has been configured. If this happens, then you're going to notice a couple of common symptoms. First of all, the host will be able to communicate correctly with other hosts on the local network segment, but the host will not be able to communicate with hosts on another network segment, including the internet. A key mistake that's commonly made, and something that you need to remember, is that the address that's assigned to the default gateway router has to reside on the same logical subnet as the host that's using it. You need to check the default gateway address and verify that it's configured with an IP address and subnet mask that's appropriate for your local subnet. And you need to make sure that it is the correct IP address. Another common problem revolves around DNS name resolution. You need to make sure that the correct DNS server address has been configured for name resolution. For example, if you find that you can ping a remote host by its IP address, but you can't ping that host by its DNS host name, then something's wrong with your name resolution system. It can be caused by several different things. One thing you should check first is whether or not the host has been configured with the correct DNS server IP address. In addition to DNS issues, you also need to be concerned with DHCP issues on an IP network. DHCP problems can cause serious protocol issues if the DHCP server is misconfigured. The DHCP server, remember, hands out IP addresses, subnet masks, the default gateway address, as well as DNS server addresses to the host on your network. When the host comes up on the network, it gets this IP address and information from the DHCP server. Now, problems can occur if that host cannot contact the DHCP server when it comes online. Modern operating systems, including Windows, Linux, and Mac OS, can let a protocol called a PIPA take over if an address can't be configured from a DHCP server. Now let's suppose we have a DHCP service running in this network, and it's built into our network switch. We've configured our workstations here to use DHCP to get their IP addressing information. Now, in most networks, our servers, our routers, and our other network infrastructure devices are usually assigned a static IP address. They don't use DHCP. In this situation, we can potentially have a problem if the DHCP server stops working. Suppose the firmware inside our switch here experiences a fault and the DHCP server goes down for some reason. When this happens, hosts can no longer get an IP address when they're powered on. So, at this point, a PIPA takes over, and the DHCP clients will get an address starting with 169.254. Now, when this happens, all of the hosts on our network that received an PIPA address can still communicate with each other, but they cannot communicate with our infrastructure devices. For example, they can't communicate with our file server, nor can they communicate with our default gateway router because they're assigned a static IP address. And because our workstations are using a PIPA assigned addresses and our infrastructure devices are using statically assigned addresses, they're now running on two different logical subnets. Really, with the PIPA, the goal is to automatically assign IP addresses to network hosts such that if something happens to the DHCP server, they still get an IP address. Now, theoretically, this should allow them to continue to operate and communicate. However, in this scenario, these three hosts will be able to communicate using their PIPA assigned IP addresses, but they'll not be able to communicate with any of our critical infrastructure devices that use statically assigned IP addresses. Now, the problem here is that being able to communicate between workstations really isn't all that useful. Users on these workstations need to be able to access their files, they need to be able to send print jobs to printers, they need to access their email, and they need to access other services that are hosted on our servers. In addition, access to the internet requires the ability to communicate with this network's default gateway router. Therefore, when a PIPA takes over, these workstations lose communications with all of these infrastructure devices. And therefore, what they can do is not a whole lot. Now, another DHCP problem that happens occasionally is that of a rogue DHCP server. Now, this can occur in several different situations. One of the most common examples is one where somebody installs a server operating system. Perhaps they're doing some testing, they've installed a server operating system in, say, a virtual machine. Now, without realizing it, they may accidentally enable the DHCP service on that server. I've even seen situations where a rogue DHCP server can be accidentally enabled by an end user who's configured their mobile phone to function as a hotspot. Now, this can disrupt network communications because some of our network hosts are going to get their IP address from the rogue DHCP server, while our other hosts get an address from a legitimate DHCP server. Now, because the rogue DHCP server wasn't configured properly, it's very likely that it's handing out incorrect IP addresses. When this happens, some workstations can communicate with the server or the router, and others can't because they're getting the wrong IP addressing information. That's it for this lesson. In this lesson, we talked about troubleshooting the IP configuration. We looked at using the correct IP addresses. We looked at using the correct subnet mask. We talked about the importance of configuring the correct default gateway router address. We talked about configuring the correct DNS server address. And then we ended this lesson by talking about how to resolve common DHCP problems.
As part of troubleshooting, I might need to verify the IP configuration of a computer. The computer I'm working on has a single network interface card. I can go ahead and right-click on the network icon, select Network and Sharing, select Ethernet, select Properties, Internet Protocol version 4, and select Properties. Here it says to go ahead and get an IP address automatically. You can see that this doesn't really give me much information. I can, however, close those property dialogues and click the Details link. Here I have the IP information that was given to me from a DHCP server. Some of the lines of interest are the DHCP enabled, yes, my IP address and subnet mask, my default gateway and the DHCP server addresses, and the DNS server address. This dialog box isn't the only place that I can get that information. Now let's close all of these. I can open up a command prompt and use the utility ipconfig. ipconfig displays a little bit of information. It gives me my IP address, my subnet mask, and my default gateway. So it's a quick and easy way to confirm that I have an IP address. I actually want a bit more information than what I see here, so I'm going to type CLS to clear my current screen. If I want more information, I'll use the command ipconfig/all. Okay, let's scroll up. Here's the information we want to look for. We have the line DHCP enabled. It says yes. So does auto configuration enabled, our IPv4 address information, our subnet mask, our default gateway, and our DHCP server. We have the DNS servers. One of the lines that we want to focus on for troubleshooting is this line right here, DHCP enabled. It's currently telling us yes. Let's go back to the properties of this network interface card and make a few changes. So go ahead and open up the properties. In this case, we'll just give it some static IP information. We'll go ahead and configure a static IP address of 192.168.0.75. We'll leave the default subnet mask. Go ahead and set up a default gateway of 192.168.0.1. This is my current router. We'll provide a static DNS server address, 192.168.0.2. Let's click OK and close all of these dialog boxes. Now we'll go back to the command prompt. We'll issue an ipconfig/all command, scroll up, and let's look at the differences. It says DHCP enabled and no, whereas before it said yes. So we're no longer asking for information from the DHCP server. We've configured it statically, and you'll see that here. The IPv4 address is now 192.168.0.75, along with our subnet mask and the default gateway that we statically configured. You'll notice that underneath our default gateway line, there is no DHCP server IP address line. We know that it's not looking for the DHCP server in this case. So let's go back to our network card and re-enable DHCP and DNS. We'll right-click on the icon, select Network and Sharing Center, select Ethernet, Properties, Internet Protocol version 4, Properties, and select Obtain an IP address automatically. We'll also tell it to obtain a DNS server address automatically. And now let's close all of these dialog boxes. Alright, now I'm going to go ahead and deactivate the DHCP server on the network. We're going to switch over to the server, and we're going to deactivate the DHCP server on the network. It says my scope is active, and disabling the scope will prevent clients from obtaining IP addresses. Are we sure we want to disable the scope? We'll go ahead and click yes, and now we'll return back to our workstation. This time we want to use the utility called ipconfig/release. Now we've released any IP addresses. We no longer have an IP address that we're given from our DHCP server or the static configuration. We'll go ahead and use the command ipconfig/renew. Our computer is sending broadcast traffic out to look for a DHCP server requesting an IP address, and it might take a little while because it doesn't know that we shut down the DHCP service. This could take some time, so I'm going to hit Control-C to cancel that. Typically, I would have a message that would state it was unable to contact the DHCP server. I'm going to go ahead and type in to clear my screen again. Now let's look at an example scenario. Say we have a computer user that gives us a call and says, hey, I can't connect to the internet. You go to his workstation and you type the ipconfig/all command. So we'll scroll up here and start to diagnose the problem. We want to notice that, yes, DHCP is enabled, so it wants to talk to the DHCP server. In this case, I'm missing the line that says DHCP server with its IP address. Instead, I have an IP address that has been given to me through auto configuration, which is known as automatic private IP addressing, or APIPA. I'll know that because all addresses assigned through APIPA have the network address of 169.254 with a subnet mask of 255.255.0.0. When you see that the DHCP is enabled, yet you have an address within this range, you'll know that APIPA has given it this IP address. This also means that if you have other computers on the network that couldn't reach the DHCP server, they'll also probably have 169.254 IP addresses. Now, before we end this demonstration, I'm going to go back into my server and activate my DHCP scope so my workstation can get an IP address. I'm back on the server, and I'll right-click on my scope and select Activate. Now let's return to our workstation one final time. I'll do an ipconfig/renew. So I see that I have an IP address, but I want more information, so I'll type in ipconfig/all, scroll up, and see the information here. You can see that we do have DHCP enabled. We also have the IP address and the rest of the information that the DHCP assigned to our workstation. In this demonstration, we're going to work with the ifconfig command to manage IP addressing on a Linux. In this demonstration, we're going to work with the ifconfig command to manage IP addressing on a Linux system. Let's open a terminal window on our Linux system. Let's go to Search Your Computer and select Terminal from these choices. I could also search the system for Terminal if it didn't show up in the list. Now, before we get started, be aware that on some newer releases of Linux, ifconfig and the rest of the NetTools have been replaced by the new IP Route 2 set of utilities. So instead of typing ifconfig to find the IP address of your computer, you type ipaddr. On my Linux system, I have already installed the old tools by entering the command sudo apt-get net-tools install to install the NetTools utilities. Now let's get back to ifconfig. ifconfig is a lot like ipconfig on a Windows workstation. Now, notice that I'm currently logged in as my dfellows user. dfellows is a standard user, not a super user. I could run the ifconfig command at the command prompt, and I'd be able to view IP configuration information, but I couldn't modify it. If you want to use ifconfig to modify configuration info, then you have to switch to your root user account first. I'll use the sudo command to switch to root. Now I'll use ifconfig. I'll type my password, and now I can do whatever I want on this system. After we type ifconfig, we see that two interfaces are displayed. We have the eth0 interface, and we have the LO interface. This interface up here is your wired or wireless network interface. This interface down here is your loopback adapter. It's the local host. Even if your Linux system doesn't have an Ethernet interface installed at all, it'll always have at least one loopback interface because various system services use that interface to communicate. Also, be aware that up here with your actual interface, your wired or wireless interface, the name of the interface may or may not be eth0. On an older or newer Linux system, it might be named something else. The interface name is defined by what type of interface it is, wireless or wired. Other factors, like whether that interface is integrated into the motherboard of the system or installed in an expansion slot, can also affect the name. If we look at the output of the ifconfig command, we can see a lot of very important information. For example, you see inet is the IP version 4 address, and netmask is the subnet mask that's been assigned to this interface. Broadcast specifies the broadcast address for the subnet that we're on. If IPv6 is running, then the IPv6 address is listed here under inet6 address. RX packets tell us how many packets have been received on this interface. There's some important statistics over here, such as errors, drops, and overruns. You can keep an eye on these parameters to see if any errors occur. We also have the transmit packets. These are the number of packets the system has transmitted, and we have the number of collisions listed too. Down here, we can see how many bytes of data we've received on this interface and how many bytes we've transmitted on this interface. As you can see, with ifconfig, you can view almost the same information that you can view with ipconfig on a Windows system. You can do some extra things with ifconfig that you can't do with ipconfig, like change the IP address or shut down an interface. Remember, to make changes, you have to enter the sudo command to switch to root. So I'm going to type clear to clear the contents of the terminal screen, and I'm going to enter sudo ifconfig eth0 down. Now let's do ifconfig and see our network interfaces. Notice that eth0 is gone. Now let's do sudo ifconfig eth0 up and enter ifconfig again. Now our interface is up again. That's it for this demonstration. In this demo, we looked at using the ifconfig command on a Linux system to view IP address configuration information. We also configured our interface to enter the down state and the up state.
In this lesson, we're going to spend some time talking about network troubleshooting. Now, network troubleshooting often starts with a help desk call from a user. Now, be aware that most of your end users are not going to have enough networking or computer knowledge to describe specific symptoms to you. Therefore, one of the first steps in the troubleshooting process that you're going to have to take is to first identify the scope of the problem. Is the problem being experienced across the entire network, or is it isolated just to a single workstation? In this example, we're going to look at a situation where we have a single user who is connected through a router to the internet, and this user is trying to access a website somewhere out on the internet. Now, when they enter the URL of the website in their browser window, they get a message basically telling them the website can't be accessed. So, in order to troubleshoot this problem, we first need to determine the scope of the problem. One of the things we can do to accomplish this is to first try and reproduce the problem ourselves. In this example, we could open up a browser on our workstation and try to do exactly what the user is doing. Alternatively, you could go to the user's desk and use their workstation to try to replicate the problem as well. So in this example, let's suppose that we try to access the same web server out on the internet and we don't get a response either. Therefore, one of the first things we might try to troubleshoot the problem at this point is to ping that web server out on the internet by its IP address. Now, in order to test IPv4 communications, we use the ping command. If, on the other hand, we need to test IPv1 to ICMP traffic, which would filter out all of our ping requests. Or it's also possible that maybe the IP protocol itself is misconfigured on the workstation. So in order to help narrow down the scope of the problem, the next thing you might try is accessing a different website on the internet. You can also try pinging other hosts on the internet. If you find that some hosts respond, but others do not out on the internet, then the problem likely exists outside of your network. It's a problem on the internet itself. If, on the other hand, you can communicate with the destination host from the source host, then you know that networking communications are working all the way from your network through the internet into the destination host. And if this is the case, really there's not much more you can do but tell the end user that they're going to have to wait until the web server comes back online. Now, on the other hand, let's suppose that you find that you can't access any hosts on the internet at all. Everything you try doesn't work. Now, this indicates that the problem resides elsewhere. This could indicate, for example, that something's wrong with your organization's network, or maybe something's wrong with your organization's connection to the internet. Now, be aware that most organizations connect to the internet through a single router, and this router connects to another router at your ISP's location. Now, the first troubleshooting step you can take in this scenario is to first try and ping your workstation's default gateway. And if you get a response back, it indicates that the router's up and the workstation can reach it. And if this connection works, then you can try pinging the interface on the other side of the router that's connected to your ISP. If you can ping this address and get a valid response back, then you know that your router itself works as well. And you also know that routing is being performed because the packet being sent to the destination network can make it back through the router to your workstation. Now, to further then test communications, we can try pinging the IP address of the ISP. In this lesson, we're going to spend some time talking about network troubleshooting. Now, network troubleshooting often starts with a help desk call from a user. Now, be aware that most of your end users are not going to have enough networking or computer knowledge to describe specific symptoms to you. Therefore, one of the first steps in the troubleshooting process that you're going to have to take is to first identify the scope of the problem. Is the problem being experienced across the entire network, or is it isolated just to a single workstation? In this example, we're going to look at a situation where we have a single user who is connected through a router to the internet, and this user is trying to access a website somewhere out on the internet. Now, when they enter the URL of the website in the browser window, they get a message basically telling them that the website can't be accessed. So in order to troubleshoot this problem, we first need to determine the scope of the problem. One of the things we can do to accomplish this is to first try and reproduce the problem ourselves. In this example, we could open up a browser on our workstation and try to do exactly what the user is doing. Alternatively, you could go to the user's desk and use their workstation to try to replicate the problem as well. So in this example, let's suppose that we try to access the same web server out on the internet and we don't get a response either. Therefore, one of the first things we might try to troubleshoot the problem at this point is to ping that web server out on the internet by its IP address. Now, in order to test IPv4 communications, we use the ping command. If, on the other hand, we need to test IPv6 communications, we can use the ping command again, just with a -6 switch added to the end. Or you can use just the ping6 command itself. Now, if you can ping the server by its IP address and it responds, but then you try to ping it using its DNS name and it does not respond, this usually indicates that we have a name resolution problem, most likely on the internet for their business, may even set up to your ISP. If you can ping this address, in case the router's up, and connect to the internet through a single router. And this router connects to another router at your ISP's location. Now, the first troubleshooting step you can take in this scenario is to first try and ping your workstation's default gateway. And if you get a response back, it indicates that the router's up and the workstation can reach it. And if this connection works, then you can try pinging the interface on the other side of the router that's connected to your ISP. If you can ping this address and get a valid response back, then you know that your router itself works as well. And you also know that routing is being performed because the packet being sent to the destination network can make it back through the router to your workstation. Now, to further then test communications, we can try pinging the IP address of the ISP's router on the other side of our router. If you can get through your network to the ISP's router, then the problem is most likely with the ISP's network. And at that point, there's not much you can do. You'll need to call the ISP and report the problem because it exists outside of your administrative domain. And in many cases, they're probably already aware of the problem and they're probably already working on it. In fact, for this reason, an organization that's completely dependent upon the internet for their business may even set up a redundant ISP. That way they can keep things running if their primary ISP goes down and has a problem such as we talked about. So at this point, let's step back a little bit and consider what we would do if the ping test to our default gateway router fails. For instance, let's say that we can ping the near side of the router, but a ping to the other side of the router that's connected to the ISP fails. In this case, you know that messages are not making it from your router to the ISP. The problem could be one of many. It could be a misconfigured router, perhaps it's a break in the line that connects you to the ISP, and so on. In this case, you may need to call the ISP and ask them to run tests to verify that the link itself is working. Now remember, the network wiring hits a certain point called the demarc at your location. Everything on your side of the demarc is your responsibility, everything on the other side is the ISP's responsibility. The ISP can run tests to verify that the line from their location to the demarc point is working. If it is, then you know you've got to troubleshoot the problem on your side of the demarc. In essence, the problem exists on our network. If the ISP's line test fails, on the other hand, then the ISP has to go troubleshoot the line from their end. Finally, let's look at one more scenario. Let's suppose that when you try to ping your default gateway router, that you find that you can't communicate with it at all. It doesn't respond to your ping request. Now, in most cases, your host workstation will be connected through a switch to the other devices on the same network. One thing you can do is try to ping another workstation on the same subnet that's connected to the same switch. Now, if you can ping one of these other workstations, but not the default gateway router, then the problem may be with the link between the router and the switch. Or maybe the router itself is misconfigured, or maybe it's down. However, if you cannot ping any other host on the network, then you probably need to focus your troubleshooting on the link between the workstation and the switch, or maybe even the IP configuration of the workstation itself. That's it for this lesson. In this lesson, we talked about how you can use the ping command to test communications with various devices inside and outside of your network to narrow the scope of a network problem. We discussed how you can use this information to identify whether the problem exists with a specific host on the internet, within your ISP's network, or with your connection to the network, or maybe within your own local network itself.
In this demonstration, we're going to work with two network troubleshooting utilities. First, we're going to look at ping, and then we're going to look at traceRT. We're going to practice using these commands on a workstation on subnet A. We're going to use these utilities to work with other hosts on the same subnet, hosts on different subnets within our same organization, and hosts out on the internet. As you can see, there are two routers between my workstation and the internet, one router here and one router here. Any traffic that goes out to the internet from my workstation must go through these two routers. The first thing we want to do is to verify our IP configuration on this workstation. Let's open up a command prompt. We'll use the ipconfig command to do that. We use the /all parameter so we can see all the available information. When we do, we see that the IP address assigned to this workstation is 192.168.0.101, and its subnet mask is 255.255.255.0. That means we're on the 192.168.0.0 subnet, and the default gateway is 192.168.0.1. And if you look here, you can see that our DHCP server has the address 192.168.0.2. We also have a DNS server with IP address of 192.168.0.2, as well as a backup DNS server out there on the internet with an IP address of 8.8.8.8. I'm going to type CLS to clear the screen. The first utility we want to practice working with is the ping utility. The ping utility sends out an ICMP echo request packet to a remote host that you specify. When that host receives the packet, it responds back with an ICMP echo response. If your system receives an ICMP echo response, that tells us two things. First, it tells us that there is physical connectivity between my workstation and the remote host that I'm pinging. And second, it tells me that the protocols are properly configured on that physical infrastructure. So the packets are making it through. Let's try using it. Let's ping a host that's on my same subnet. Let's go ahead and try to ping my DNS server. So let's ping 192.168.0.2. When I do, 4 ICMP echo request packets are sent to 192.168.0.2, and 4 ICMP echo response packets are received in return. Now there's a lot of good information we can pull from the output of ping. This parameter right here tells us how big the ICMP echo request packet was in bytes. The time parameter over here tells us how long it took from the time that we sent the ICMP echo request to the time that we received the ICMP echo response. As you can see, each one took around a millisecond. Some summary statistics are displayed down here. We sent 4 requests, we received 4 responses. 0 were lost. You will on occasion have instances where you may send 4 requests and get 3 responses back and lose 1. That could be caused by network congestion, bad network cards, and all kinds of different things. So if that happens, you may need to do some troubleshooting. We also have some averages for our round trip time. The response was basically almost instantaneous, 1 millisecond, because we're on the same subnet. Notice up here that we pinged by the IP address of the remote host. You don't have to do that. You can also ping by domain name. So let's try that. Ping corpnet.xyz. Notice that ping first resolves this host name into the associated IP address. Then it sends the same 4 ICMP echo request packets to the remote host. Pinging by IP address first and then by DNS name can be very valuable. The reason is because if you can ping the remote host by IP address but can't ping by its DNS name, it tells you that the basic connectivity is there, the protocols are working. But we may have a problem with our name resolution system. Maybe we have the wrong DNS server address configured, or maybe our DNS server is down. Maybe it doesn't even have a record for the host that we're trying to ping. Let's go ahead and clear the screen. We know everything is working well so far, so let's go ahead and send a ping through this router out onto the internet. We'll type ping, and then we'll type the DNS name of a server out on the internet. It's testout.com. DNS will resolve testout.com into the appropriate IP address. We'll send the 4 ICMP echo request packets. Again, we got all of our responses for each of those packets back, meaning that we have good connectivity out to the internet. Notice that there's something different right here. Our round trip time is much slower. That's because these packets had to go through 2 of our organizational routers. Then they went out onto the internet and went through many different routers, probably 8 or more, before they finally reached the destination host. The ping packets had to travel such a long distance that the round trip time was considerably longer. We can see that down here in the summary statistics. At this point, let's shift gears and look at the traceRT utility. Ping is awesome for testing connectivity between 2 hosts, but it doesn't reveal much about the path a packet has to take through various networks between the sending host and the destination host. If you need to troubleshoot routing problems, then you need to use the traceRT command. Now be aware that on Windows, this command is spelled traceRT, and on Linux systems, it's traceroute. Also, be aware that the way traceRT works is a little different on Linux and Windows. On Windows, it uses the ICMP protocol just like ping. On Linux, it uses the UTP protocol instead of ICMP. TraceRT is interesting. It uses the same ICMP echo request packets as ping. However, it manipulates that ICMP echo request packet a little bit to reveal the IP address of each router between the source sending system and the destination system. It does that by manipulating the time to live parameter, the TTL. We don't want packets circling the internet endlessly because they couldn't reach their destination host. The ICMP protocol is designed so that every time a packet has to cross a router, the router will automatically subtract the value of the TTL by 1. If this number gets down to 0, we can pretty much assume that the packet is going nowhere. Instead of letting it circle the network endlessly, we just drop it. So let's test this out. We'll just do a traceRT between this system right here and my default gateway right here. First, we'll do this with the IP address. They're on the same subnet, so we really shouldn't see a whole lot happening here. Now let's do a traceRT using our domain name. Let's do traceRT corpnet.xyz. As you can see, we got one hop right here. We see the DNS name and IP address of this first hop router. So now let's do something a little more complex. I'm going to clear my screen by typing CLS. Now let's do a traceroute to www.testout.com. This is going to require a little bit of time to complete because we're going to send packets to a host out on the internet. It'll have to hop through several different routers before it finally reaches the destination system. Now we're seeing many hops delivered by the traceRT command. You'll notice right here, we have the same first hop that we looked at before. Now it continues going through routers or hops to the destination device. Each router it goes through is called a hop. Sometimes you'll see a message from one of the routers that says, request timed out. This usually means that the router is configured not to respond to ICMP echo requests in order to prevent denial of service attacks. Traffic is going through it just fine. It's just ignoring all the ICMP traffic that's sent to it. You can see that in order to get to testout.com, a packet has to move through 5 different routers. Okay, so there are 5 hops between my system and testout.com, with this last IP address being the end device. Normally, you don't count the last device as a hop since it's not actually a router in most cases. With this information, you can troubleshoot problems if you're not able to reach hosts out on the internet. For example, if this router right here were down, the second hop, then we would see no output for the rest of the routes all the way down because none of the packets were making it past this router. That can help us say, oh, okay, I know where to start troubleshooting because I know that this router is working just fine. The problem is with this guy right here. Okay, that's it for this demonstration. In this demo, we practiced 2 very useful troubleshooting tools. First, we looked at ping, and then we looked at traceRT. In this demonstration, we're going to look at how to use two useful network management utilities, ARP and netstat. Let's start this demo by looking at the ARP utility. ARP stands for Address Resolution Protocol. The ARP utility is used to view and manage the ARP table on an IP host. Remember, whenever we send a packet to a destination host on an IP network, we have to know that host's MAC address. Every network interface has a MAC address. The MAC address is the hardware address that's burned into the ROM on a host network interface. The issue here is that the MAC address doesn't change. It's associated with a specific network interface. There are some rare cases where this isn't true, but that MAC address is usually globally unique, meaning that no two hosts in the world should have the same MAC address. IP addresses, on the other hand, are logical addresses, meaning that a host could have one IP address one day and a completely different IP address the next day. Therefore, we have to map IP addresses to MAC addresses so we know which physical interface a particular packet needs to be delivered to, and that's the job of the Address Resolution Protocol, or ARP. The ARP utility is used to manage the ARP protocol. It can be used to view mappings of IP addresses to MAC addresses on a particular host. It can also be used to add or remove mappings of IP addresses to MAC addresses on a particular host. Let's take a look at how it works. If we want to just view a current list of IP address to MAC address mappings, the ARP table on a host, we simply enter ARP-A at the command prompt of the Windows system, and we can see here that we have several different mappings. Notice that we have a mapping for 192.168.0.2 that maps to this physical address, this MAC address, and it was dynamically discovered, meaning that when a packet was sent out to the 192.168.0.2 host, the ARP protocol sent out a broadcast saying, okay, which one of you has the IP address 192.168.0.2? The host with that IP address responded back saying, hey, here's my MAC address, and the ARP protocol recorded that mapping in the ARP table on this host. That's why it's dynamic in nature over here under type. If necessary, you can also use the ARP utility to either add or delete a mapping to the ARP table on a Windows host. For example, let's suppose that this device has been swapped out. Of course, my new device's network interface is going to have a different MAC address. My new device has the same IP as the old device, but we need to update the MAC address. Let's look at how this is done. In order to remove an entry from the ARP table, I do have to have administrator privileges on in the command window, so let's go ahead and gain administrator privileges. I'll right-click on the Start button, go up here, and select Command Prompt Admin. Say yes to this, and then let's move this up a little bit. We want to delete the mapping 192.168.0.100, which is a Linux server on my network. So we enter ARP-D 192.168.0.100. And then we enter ARP-A again. You can see that the mapping was deleted from our ARP table on this workstation. We can add it back in a couple of different ways. One way is to simply send a ping packet to the destination host, such as ping 192.168.0.100. When I do this, the ARP protocol is going to look in the ARP table and say, oh, I don't have a mapping for that IP address, I need to go get it. It'll send out a broadcast saying, hey, which of you has an IP address of 192.168.0.100? The host will respond back with its MAC address, and then the ping command will go ahead and send the ping packet. If we do an ARP-A, you can see that 192.168.0.100 has been added back into the ARP table of my system. You could do it manually if you wanted to. If you knew the MAC address of the host and you wanted to add it in manually, you could use the ARP-S command followed by the IP address of the host, 192.168.0.100, followed by a MAC address of the host. It would look like this, ARP-S 192.168.0.100, followed by the MAC address. When I press enter, ARP would manually add this IP address mapping into the ARP table. I'm not going to do this because it's already there from when I pinged that address. So that's how ARP works. Let's clear the screen by typing CLS. The next utility we want to look at is the netstat utility. Netstat stands for Network Statistics. It's a command line utility that you can use to display information about the network interfaces in your system. You can view information about network connections, view the routing table, look at protocol statistics for each network interface you have installed in your system, and so on. Let's begin with just the basic netstat command. The netstat command without any parameters will display a list of active connections with this host, both incoming and outgoing. Let's put in netstat and press enter. You can see that I have several established connections. Now let's enter netstat-A, and let's scroll up. The -A option will display a list of not only all connections, but also all of the open ports on your system that are currently listening. This could be really useful because it's a great way to find rogue processes. If you have some type of malware running on your system that's opened up an IP port and is either sending or receiving information, this is one way that you can identify it. The netstat-A gave us a list of all of the open connections and open ports on the system, ports that are listening for connections. This connection right here, 192.168.0.101, using the TCP protocol on port 139, is actually a mapped drive to a share on my CorpNet DC1 server. Notice we also have several other open ports that are in a listening state, and you can come over here and see what the port number is. If you see something you don't recognize, you can research it and find out if it's a legitimate open port or if it's not. We also have our active listening UDP ports down here as well. In addition to detecting malware, the netstat-A command is also a useful tool for verifying that a network service is running the way it's supposed to. For example, let's say you start up a particular service and you're not able to establish connections to it from a remote host. You've checked the firewall and the firewall has the port open. You can come in and use the netstat-A command to see if the port is actually open and listening on the host, and that'll help you troubleshoot what might be wrong with the service. Let's do a CLS to clear out our screen. In addition to the -A option, you can also enter netstat-ES to display Ethernet statistics for each protocol configured on your network interface. If we scroll up a little bit here, you can see a ton of information about the various protocols for your network interfaces. For example, up here, you have a summary of interface statistics. For example, the number of bytes sent and the number of bytes received, the number of unicast packets sent, the number of non-unicast packets, packets that were discarded, errors and unknown protocols, and so on. There is a lot of useful information here for troubleshooting. So once again, let's clear the screen. You can also use the netstat command to view your routing table. We'll enter netstat-R, and let's scroll up a little. This will show you both IPv4 and IPv6. We're not going to talk about IPv6 right now, but it will display the routing table for both protocols. Here you can see your IPv4 route table. This is the same information that you can get by entering the route print command. We have a route here for the local network segment, 192.168.0.0, and we have the default route here, 0.0.0.0. Any packets not addressed to a host on the 192.168.0.0 network will immediately be sent to the default route up here, which is then forwarded to the 192.168.0.1 default gateway. That's it for this demo. In this demo, we analyzed and configured the ARP and netstat tools.
In this demo, we're going to look at TCP dump. TCP dump is a free open source command line utility that captures network traffic on Linux systems. TCP dump works a lot like the popular packet capturing program Wireshark, but many network administrators prefer TCP dump because it works in the terminal. TCP dump prints out all the traffic it captures in your terminal. You can filter the packets using various expressions and save the captured packets for later analysis. I have a Linux system running here, and I want to open the terminal. I can do this by going up to search your computer, typing in terminal, and hitting enter. Once the terminal appears, I want to install TCP dump. I have to do this as a super user or sudo. So to install, I'm going to type sudo apt get install TCP dump and press enter. It asks for my password and I'll type it in here. You can see here that TCP dump is already installed with the newest version. If it wasn't installed, it'll install it. If an older version's installed, it'll just update to the newest version. I'm going to type clear to clear the screen. Before we talk about how to use TCP dump, the first thing you'll want to be aware of is the command to display the manual, man TCP dump. You can read through this manual and see all the different expressions that can be used. Toward the bottom, you can also see examples of the different ways to use TCP dump. If this manual is hard to read, you can find the exact information from the official TCP dump website at www.tcpdump.org. We don't have time to go through every single example, but we'll cover a few here. Let's jump right in and start to capture traffic. To do this, I need to know what my network adapter is called. I can quickly type in ifconfig, which displays my IP address, but also shows me the name of my network adapter. I can see that it's called eth0. That's what I will need to know. For the first command, we're going to tell TCP dump to capture traffic on our network interface. The interface is identified by -i and then the network adapter. It also requires super user privileges to run. So let's type in sudo TCP dump -i eth0 and press enter. Once we press enter, TCP dump starts to capture network traffic going through my network interface card, but there isn't much going on yet. Let's open a web browser to create some traffic. As you dump starts to capture that traffic. To stop the capture, I can press Ctrl+C. You can see that in just a few seconds we were able to capture 292 packets. 549 were received by filter, and 257 were dropped by the kernel. And you can see that we've captured some web traffic, mostly HTTP and HTTPS, from when we opened our web browser. Okay, so far we have looked at capturing network traffic that has traveled through my network adapter on this system. But what if we wanted to capture traffic from another computer or our entire network? We know our network switches don't forward traffic to all ports, only to the destination ports based on the physical address, or MAC address. So I've turned port mirroring on for my switch. We're not going to learn how to do that in this demo, but I wanted you to be aware of what I've done in the background. So we have port mirroring enabled on the switch port where my Windows 10 workstation is plugged in. Now, all the traffic from that network interface card is going to get captured here with TCP dump. If you're a student or studying for a certification exam and practicing these skills at your workplace or school, make sure you're not violating any of the organization's policies. You are, after all, capturing potentially confidential network traffic. I'll clear the screen again. Alright, I'm going to start capturing some traffic again here, but a few things are different. I'm also capturing from my Windows 10 workstation, and I'm going to just focus on just FTP traffic, which runs on port 21. To do this, I'm just going to type in sudo TCP dump port 21 and press enter. Now I'm capturing only FTP traffic. Not much is going to happen until my Windows 10 machine uses FTP. So let's jump over to my Windows 10 system and create some FTP traffic. I'm on my Windows 10 system and I'm going to open a web browser and go to a common FTP site on the internet, which is ftp.hp.com. This is where you can get files such as printer drivers. I'll click around here just to generate traffic. That's good enough. I'll close this window. Now let's go back to our Linux system and see what's going on with TCP dump. I'm back on this Linux system. You can see a lot's happened, but when you look, everything is isolated to just FTP traffic. I can see the timestamp, hours, minutes, seconds, and milliseconds. I can see the name of the Windows 10 PC that I was on and the address of the FTP we were at. If this site required me to enter some sort of credentials, those would have been captured and displayed in clear text, since FTP traffic isn't secure. Once again, there's a lot of uses for TCP dump along with lots of expressions that can be used to narrow your results. It's not as popular as some other packet capturing utilities and software, but it's still very useful to network admins. That's it for this demo. In this demo, we learned how to install and update TCP dump. We looked at the manual, where you can find a list of expressions that can be used. We practiced capturing some traffic on our Linux system, and used port mirroring to capture traffic from a Windows system on our network.
sumo. Sumo, sumo. Sumo, sumo.
Why must we wrestle? Why not live in peace?
Together in peace.
I won't hurt you. Just dress you up like Grandpa. Yes.
But I don't want to be Grandpa! You don't get to get off my lawn!
spend some time talking about fixing problems with the DNS service in your network. As you know, before two IP hosts can communicate using host names, we have to take those host names and resolve them into IP addresses that the IP protocol itself can understand. Now, the job of a DNS server is to resolve these host names, such as www.google.com, into an IP address. And it also can work in reverse. It can take an IP address that we give it and resolve it into its associated host name. Now, a common symptom of name resolution problems is one where users on your network open up a web browser and they try to access a web page out on the internet, and when they do, they just get an error message. Something is displayed saying essentially, I can't reach the server, because the IP protocol has no idea where it's supposed to go. It can't locate the server. Now, a quick and easy way to test DNS name
I am taking you off my Christmas list.
Oh no.
resolution is to try pinging a host by its IP address. If you can ping by the host IP address, then you know that basic connectivity exists between those two systems. Once that's done, then try pinging that same host, but this time using its DNS name. This time, if the ping fails, then we know that there's a pretty good chance that we have a DNS name resolution problem. We know that network connectivity exists between the sender and the receiver, it's just that the sending host can't figure out how to resolve the host name into an IP address that it can work with. There are many possible causes for DNS problems. For example, the DNS server could be down or just otherwise unreachable for some reason. You can try using ping to test communications with the DNS server itself to see if it responds. However, if you do this and you don't get a response, be aware that the firewall protecting the DNS server may actually be configured to drop ICMP packets in order to prevent denial of service attacks. So, if this happens and you try pinging the DNS server and it doesn't respond, don't immediately assume that the server's down just because it didn't respond. It could be that there's a firewall in the way that's simply filtering out all of your ping packets. It's also possible that there could be a routing problem between the sending host and the DNS server. In this situation, you can use the traceroute command to test the route between the sending host and the DNS server. It's also possible that the sending host could be configured with the wrong IP address for the DNS server. In this case, you can use the nslookup or the dig command to test whether or not the IP address that you have configured on your workstation is actually the correct DNS server. Now, be aware that it's possible that your workstation is configured correctly and that the DNS server is configured and working correctly as well, but for some reason that DNS server is unable to contact a root-level DNS server. And this could be due to several different things. It could be due to a routing problem, it could be a connectivity issue, maybe there's a WAN link issue. To test this, you need to do two different things. First of all, try using nslookup or dig to resolve a DNS name that you know that your DNS server is authoritative.
There was only one left and he ate it.
So that means you have to turn into a tank and blow him up?
Yeah? What?
authoritative for. Because the DNS server is authoritative, it should actually have a local record for the hostname. And if name resolution fails, at that point we know that the DNS server itself is having some problems that we're going to have to troubleshoot. If it's successful, however, and it is able to resolve a hostname that it's authoritative for, the next step is to try using NSLOOKUP or dig again, but this time send it a DNS name to resolve that it is not authoritative for. In this situation, the DNS server has to contact root level name servers and then use the recursion process to try to find the correct IP address for the hostname. If your DNS server can resolve local hostnames but cannot resolve hostnames that is not authoritative for, then you know that there's a connectivity problem, most likely between the DNS server and the root level name servers. That's it for this lesson. In this lesson, we talked about troubleshooting name resolution problems. We looked at several common DNS issues, such as an unreachable name server, routing problems between you and the name server, misconfigured DNS server addresses on host, and finally, we looked at root level DNS server communication problems.
In this demonstration, we're going to look at two utilities you can use to test name resolution with your DNS server system. The first utility is called NSLOOKUP, and the second utility is called dig. Before we go any further, I want to point out that NSLOOKUP is available on both Windows and Linux platforms. However, by default, dig is only available on the Linux platform. Before we do anything with these utilities, I want to check the IP configuration of my Windows workstation to make sure that it got the correct DNS server address when it received its IP addressing configuration from the DHCP server. To do that, at the command prompt, I'm going to type ipconfig/all. If we scroll up here, we should see that the DNS server address is set to 192.168.0.2. That's what we want, so it's working correctly. If we want to test whether or not our DNS server is able to resolve hostnames properly, we can enter NSLOOKUP at the command prompt. You actually have two different modes that you can run NSLOOKUP in. First, there's passive mode. You simply provide the hostname you want resolved, such as NSLOOKUP corpnet.xyz. In this case, NSLOOKUP will send the query to the DNS server for the hostname that you specify, return the response it gets from the DNS server, and exit out. That's one way to use NSLOOKUP. You can also use it in interactive mode, in which case you just enter NSLOOKUP at the prompt. Here you can enter as many hostnames as you'd like and have NSLOOKUP continually resolve them until you're done. When you're done, you can enter exit at the caret prompt to exit out of NSLOOKUP. Let's enter NSLOOKUP. After we do that, you'll notice I can see the hostname and address of the DNS server that this workstation is going to use to resolve hostnames. The DNS server address is 192.168.0.2, and its hostname is corpnet.dc1.corpnet.xyz. Let's use that DNS server to resolve corpnet.dc2.corpnet.xyz. I'll just spell out the fully qualified domain name and press enter. It sends that domain name to the DNS server, and it responds with the IP address that's been assigned to that hostname. In this case, that's 192.168.0.3. In addition to resolving hostnames in zones that this this DNS server is authoritative for, we can also look up names that it's not authoritative for. For example, I could enter the prompt testout.com. The response we get says non-authoritative answer. We didn't get that up here because the CorpNet DC1 DNS server is authoritative for the corpnet.xyz zone, but it is not authoritative for the testout.com zone. Notice it was still able to resolve this DNS name into the IP address. How did it do that? It could because the DNS server is configured with root hints. These are IP addresses of root-level DNS servers on the internet that are pre-configured to send queries to domain names that they're not authoritative for. In this case, this DNS server was not authoritative for testout.com, so it sent that query to a root-level name server, which in turn pointed the CorpNet DC1 DNS server to the DNS server that is authoritative for testout.com. My DNS server then sent the request to the DNS server that's authoritative for testout.com and asked it to resolve the hostname. That remote server resolved the name and sent the response back to my DNS server, which returned it to my workstation through the nslookup command. We'll exit here. So that's how you use nslookup. Now we'll switch over to our Linux system. Let's look at a second utility called dig. Like I said earlier, the dig command isn't available by default on Windows systems, but it is available by default on Linux systems, and nslookup is available on both platforms. To use dig, I've switched over to an Ubuntu desktop Linux system, and we'll use it to send DNS name resolution queries to our CorpNet DC1 name server. Just as I did with the Windows system, I want to make sure that my IP configuration is set properly. I'll use the ifconfig command at the command prompt of the Linux system. We can see that we're getting an address 192.168.0.100 from my DHCP server. Notice, however, that there is no DNS information there. The DNS information is stored in a file called resolve.conf on Linux systems. To view the contents of that file, I can enter cat/etc/resolve.conf at the command prompt, and my DNS information is viewable down here. I'll type clear to clear my screen. If I enter dig at the command prompt, it will, by default, use whatever name server is specified in the /etc/resolve.conf file. If, however, I wanted to use a different DNS server for some reason, I can still do that by entering an @ sign after the command, followed by the IP address of the DNS server that I want to use. For example, on the remote subnet, I do have a DNS server that has an IP address of 192.168.1.10. If I wanted to use it instead of my Windows server, 192.168.0.2, I would put @ sign and then the IP address of that server on the same line. Then all my name resolution requests would go to that server instead of the default name server specified in the resolve.conf file. For now, I don't want to do that. I just want to use my 192.168.0.2 name server. I enter dig at the command prompt, followed by the type of lookup I want to perform. For example, I could enter A to do an A record lookup, followed by the DNS name that I want to look up. For example, corpnet dc2.corpnet.xyz. It'll perform an A record lookup on that hostname. If, on the other hand, I want to perform a reverse lookup by looking up the pointer record, the PTR record, in the reverse zone, I enter dig PTR, followed by the IP address of the host that I want to do the reverse lookup on. Instead of resolving the hostname into the IP address, it'll resolve the IP address into the hostname. I can also perform a CNAME lookup or alias lookup by entering dig CNAME at the command prompt, followed by the alias that I want to resolve into a hostname. If I want to resolve a mail server record, I enter dig MX, followed by the domain name of the mail server that I want to resolve. For our purposes today, let's just resolve an A record. I'll enter dig corpnet dc1.corpnet.xyz. Press enter. This sends the query to the name server. It responds with the corresponding record from the zone. Notice that compared to nslookup, dig displays a little more information. For example, down here we have the question section. In other words, this is the request for name resolution that I sent. I sent this domain name. I'm looking for an internet record, and I'm looking for an A record. In response, here's what I received. Corpnet dc1.corpnet.xyz resolves to 192.168.0.2. Down here we see the query time, how long it took to make that resolution, in this case 1 millisecond, and then the IP address for the server that was used to resolve the domain name into the IP address. Notice there's a number 53 over here. It specifies that the DNS server is listening on port 53, which is the default port used by DNS servers. Then the timestamp or the response, and then the size of the message. Let's clear our screen. Now let's do a non-authoritative lookup. We just do the same thing, dig. I'll point out here that if you don't specify a type of lookup to perform, by default, dig will perform an A record lookup. So in this case, I don't actually need to include the A here. I enter dig, and let's do testout.com, and hit enter. Just as with nslookup, the DNS server receives the response, recognizes that it is not authoritative for that zone, and goes out and queries a root-level name server on the internet, which responds with the IP address of the DNS server that is authoritative for the testout.com zone. My DNS server then sends that name resolution request to the server that is authoritative for testout.com, receives the response, and then forwards the response down to the dig command on my Linux workstation. You can see here that we have the same information. Here's the question that was sent, testout.com. Just as before, we have our DNS server on port 53 and the timestamp. As I mentioned earlier, because we didn't specify a particular type of lookup to perform, by default, dig performed an A record lookup. Then we got our answer that told us testout.com resolved to the IP address of 67.192.129.239. That's it for this demonstration. In this demo, we talked about using nslookup and dig to perform both authoritative and non-authoritative DNS record lookups. In this demonstration, we're going to look at two utilities you can use to test name resolution with your DNS server system. The first utility is called NSLookup, and the second utility is called... Before we do anything with these utilities, I want to check the IP configuration of my Windows workstation to make sure that it got the correct DNS server address when it received its IP addressing configuration from the DHCP server. To do that, at the command prompt, I'm going to type ipconfig/all. If we scroll up here, we should see that the DNS server address is set to 192.168.0.2. That's what we want, so it's working correctly. If we want to test whether or not our DNS server is able to resolve hostnames properly, we can enter NSLookup at the command prompt. You actually have two different modes that you can run NSLookup in. First, there's passive mode. You simply provide the hostname you want resolved, such as NSLookup corpnet.xyz. In this case, NSLookup will send the query to the DNS server for the hostname that you specify, return the response it gets from the DNS server, and exit out. That's one way to use NSLookup. You can also use it in interactive mode, in which case you just enter NSLookup at the prompt. Here you can enter as many hostnames as you'd like and have NSLookup continually resolve them until you're done. When you're done, you can enter exit at the caret prompt to exit out of NSLookup. Let's enter NSLookup. After we do that, you'll notice I can see the hostname and address of the DNS server that this workstation is going to use to resolve hostnames. The DNS server address is 192.168.0.2, and its hostname is corpnet.dc1.corpnet.xyz. Let's use that DNS server to resolve corpnet.dc2.corpnet.xyz. I'll just spell out the fully qualified domain name and press enter. It sends that domain name to the DNS server, and it responds with the IP address that's been assigned to that hostname. In this case, that's 192.168.0.3. In addition to resolving hostnames in zones that this DNS server is authoritative for, we can also look up names that it's not authoritative. As a network administrator, you need to know how to access and configure a network switch. Now, there are two general categories of network switches: unmanaged and managed. Unmanaged switches are low-end switches that are sold in most retail stores. To set up unmanaged switches, you plug them into a power outlet and then connect your network devices using UTP cables. While these switches are you plug them into a power outlet sold in most retail stores. To set up unmanaged switches, you plug them into a power outlet and then connect your network devices using UTP cables. While these switches are convenient and easy to get up and running, they don't have a lot of the advanced management and security features available on managed switches. Managed switches need to be configured before you can use them, so let's take a look at how this is done. We're going to be using a Cisco managed switch since they're found in most networks. There are two ways to connect a Cisco switch. Out-of-band management. With out-of-band management, we configure a dedicated channel for accessing a network device. On a Cisco switch, you do this by connecting a notebook or workstation system to its console port. This is the option you need to use if you're configuring the switch for the first time because it doesn't have an IP address or any authentication information configured by default. In-band management. With in-band management, you use a standard network connection configured by default, IP address, or any authentication information configured by default. In-band management. With in-band management, you use a standard network connection to access the switch using remote access protocols such as Telnet or SSH, or using a browser-based configuration interface. This can only be done after the switch has been initially configured with an IP address and with authentication information using out-of-band management. You should avoid using Telnet as an in-band management solution because it sends all data, including authentication information, as clear text over the network connection. If you're using a web interface, you should use HTTPS instead of HTTP for the same reason. Let's assume that we're implementing a new network switch, so we need to use out-of-band management to access and configure it. This means we need to connect to the console port on the switch. Every Cisco device has a console port. You connect one end of a console cable to this port, and the other end to your notebook or workstation. When creating your network documentation, you'll depict a console connection using a dotted line. This indicates the connection is an out-of-band, dedicated connection, and not a traditional network connection. Let's take a look at a console cable and console port on a Cisco switch. Console cable used to come with every Cisco device, but now you need to buy them separately. The console cable is also called a rollover cable. You connect the RJ45 jack on one end to the console port on your switch. It indicates the connection line. This indicates the connection is an out-of-band, dedicated connection, and not a traditional network documentation. You'll depict the console connection using a dotted line. This indicates the connection is an out-of-band, dedicated connection, and not a traditional network connection. Let's take a look at a console cable and console port on a Cisco switch. Console cable used to come with every Cisco device, but now you need to buy them separately. The console cable is also called a rollover cable. You connect the RJ45 jack on one end to the console port on your switch. You connect the serial connector on the other end to your laptop or workstation. Many newer laptops and workstations don't have a serial port, so the device manufacturer provides rollover cables with USB connectors instead of serial connectors. After connecting the USB connector on the cable to a USB port on your workstation, you can load the appropriate USB driver software to enable it. The console port on a Cisco device is shown here. This is where you connect the RJ45 end of your rollover cable. After creating the physical connection between your workstation and the console port of the Cisco device, you need to load terminal emulation software and create a logical connection to the device. Some commonly used terminal emulation programs include PuTTY or Secure CRT. Configure the terminal emulation software to establish a connection between your workstation and the console port of the Cisco device. You need to load terminal emulation software and create a logical connection to the device. Some commonly used terminal emulation programs include PuTTY or Secure CRT. Configure the terminal emulation software to establish a session using the serial port or USB port on your system. By default, there are no passwords configured on a Cisco switch. You just press Enter several times to display the device prompt. So, that's a quick look at how to connect to a managed Cisco switch. To review, we discussed how to access a Cisco device, including out-of-band and in-band connections. The console port is used for an out-of-band connection to the device and is used for a first-time configuration. Once the device has been configured with an IP address and is reachable across the network, you can use in-band how to access a Cisco device, including out-of-band and in-band connections. The console port is used for an out-of-band connection to the device and is used for a first-time configuration. Once the device has been configured with an IP address and is reachable across the network, you can use in-band connections utilizing remote access protocols like Telnet or Secure Shell or a browser-based configuration interface to configure the device.
In this demo, we're going to provide an introduction to the Cisco Command Line Interface, or CLI. We'll take a look at default terminal emulation settings to gain access to a Cisco console port. We'll take a look at basic navigational commands to get in and out of different modes on the